Hello everyone. So this is the continuation of the video that I posted in your MVLE. So we will continue the discussion in polyphase. Let's start with the star or Y connection. In this method of interconnections, the star ends of three coils, so it could be finishing ends, are joined together at point N or at point S, shown in figure 19.10 or in this figure. The point N is known as the star point or the neutral point. The three conductors meeting at point N are replaced by a single conductor known as neutral conductor as shown in the second figure. So this figure is known also as four-wire three-phase system. If this three-phase voltage system is applied across a balanced symmetrical load, the neutral wire will be carrying three currents which are exactly equal in magnitude but are 120 degrees out of phase with each other. Therefore, their vector sum is 0. So for line ER, this one, it has a current which is the phase current IR, line EB which has a phase current of IB, and also EY has a phase current of IY. If we are going to add vectorially all of these currents, it will result to 0 because they are balanced. The neutral wire in that case may be omitted, although its retention is useful for supplying lighting loads at low voltages. The potential drop between any terminal or line and neutral or star point gives the phase or star voltage, but the potential drop between any two lines gives the line-to-line voltage or simply the line voltage. So for this case, this is our phase voltage which has a single subscript which is ER connected to the neutral. Also, we have a phase EB and phase EY. So we have a three-wire here. This is the phase voltage or line R, line Y, and line B. So, depende kung ano yung ilalagay nyong names dito. It can be A, B, or C. RYB or line ABC. For the first line, we have a phase voltage of ER that is equal to ER. The second line has a phase voltage of EY. The third line has a phase voltage of EB. Line-to-line voltage is the line or the voltage between the two lines. So for first line and the second line has a line voltage of ERY. So EL for line voltage, that is ERY. For the second line to line is EYB, and the third one is EBR. So if we are going to draw its vector diagram, we'll have, so for the sake of our discussion, instead of using RYB, we will use ABC. Okay? For phases, voltage phases EA, EB, and EC. Line voltages EAB, EBC, and ECA. So for positive sequence, if we rotate these vectors, with respect to the reference x-axis. Counterclockwise, we will have a positive sequence equal to, at initial, we have A at the reference, and then it will rotate counterclockwise, the next one in phase with the reference x-axis is B, and then it will rotate again at 240 degrees. You will have C. Again, at initial reference, we will have A, which is angle 0. Next one is B. It will rotate 120 degrees after A, and then C, 240 degrees after B. So you will have a positive sequence ABC. Next is for the negative sequence, clockwise direction. Again, our reference is x-axis. Initially, you will have A at angle 0, and then you will rotate this vector. The next one will be this vector C. It will go to the reference, and then next one is B. So you will rotate this A, B, C into clockwise direction, and you will get ACB. Next one is the values of phase currents. When considering the distribution of current in a three-phase system, it is extremely important to bear in mind that number 1, the arrow placed alongside the currents RYB flowing in three phases indicates the direction of currents when they are assumed to be positive and not the directions at a particular instant. It should be clearly understood that no instant will all the three currents flow in the same direction, either towards or inwards. The three arrows indicates that the first current flows toward in phase R, then after a phase time of 120 degrees, it will flow outwards from phase Y, and after further 120 degrees, outwards from phase B. Number 2, or letter B, the current flowing outwards in one or two conductors is always equal to the flowing inwards in the remaining conductor or conductors. So in other words, each conductor in return provides a return path for the currents of the other conductors. So in the figure, there are three phase currents having the same peak value of 20 amperes but displaced from each other by 120 degrees. So at instant A, the currents in phases R and B are each positive 10 amperes, such that flowing outwards, whereas the current in phase Y is negative 120 degrees, such that flowing inwards. In other words, at the instant A, phase Y is acting as the return path for the currents in phases R and B. At instant B, IR is equal to positive 15 amperes and IY is at positive 5 amperes, but IB is at negative 20 amperes, which means that now phase B is providing the return path. So at instant C, IY is equal to 15 amperes and IB is equal to 5 amperes and IR is negative 20 amperes. Therefore, the phase R carries currents inwards whereas Y and B carry currents outwards. Similarly, at point D, IR is equal to 0, IB is 17.3 and IY is negative 17.3 amperes. In other words, current is flowing outwards from phase B and returning via phase Y. So in addition, it may be noted that although the distribution of currents between the three lines is continuously changing, Yet at any instant, the algebraic sum of the instantaneous values of the currents is 0. Next is the voltages and currents in Y connection. So the voltage induced in each winding is called the phase voltage, and current in each winding is likewise known as the phase current. However, the voltage available between any pair of terminals or outers is called the line voltage, and the current flowing in each line is called the line current. So as seen in figure 19.12a, in this form of instantaneous or of interconnection, there are two phase windings between each pair of terminals, but since their similar ends have been joined together, they are in opposition. Obviously, the instantaneous value of the potential drop between any two terminals is the arithmetic difference of the two phase EMFs concerned. However, the RMS value of this potential drop is given by the vector difference of the two phase EMFs. So the vector diagram for phase voltages and currents in a star connection is shown in 19.12b. Where a balanced system has been assumed, it means that ER, the phase voltage ER, is equal to EY is equal to your phase voltage. Or in our examples or in your exams, we will use the ABC. So phase voltage EA will be equal to phase voltage EB and equal to phase voltage EC, that is your phase EMF. The line voltage VAB between line 1 and 2 is the vector difference of EA and EB. Line voltage EBC between line 2 and 3 is the vector difference of phase EB and phase C. The line voltage between the VCA or between line 3 and line 1 is the vector difference of phase voltage EC and EA. So we have here our lines. For line 1 is line A, line 2 is line B, and line 3 is line C. These are our phase voltages, line A, line B, and line C. Your line-to-line voltage will be from line 1 to line 2, that is VAB. Line 2 to line 3 is VC. And line 3 to line 1 is ECA. So EAB is equal to EBC equal to ECA, that is your line voltage. Your line currents, IA is equal to IB is equal to IC is equal to your phase current and also equal to your line current. So this is the vector diagram of your phase voltages, and we will solve or we will calculate the relationship between the phase voltage and the phase, or the phase voltage and the line voltage. So as we said earlier, that your line voltage EAB is the difference, vector difference of voltage EA and phase voltage EB. So that is EA minus EB. In the vector diagram, line negative EB is just the negation of your positive EB. So this is positive. We will get the negation of this one, and it will be 180 degrees with respect to positive EB. So this will be your negative EB. If we add these two, vectors, we will get voltage EAB. So that is equal to, let's say we have 1 angle 0 minus 1. This one is the direction. Okay? 1 angle negative 120. So we will get square root of 3 angle 30 degrees. So if you add this two, or the difference of EA and the negation of EB, we will have your EAB. So this will now the resultant. EAB. Same procedure in EBC. So EBC, we have EB minus EC. So your EC is the negation of your positive EC. So nandito siya, 180 degrees. And if we will going to get the difference between the two phase voltages, we will get square root of 3 angle negative 90. So this negative 90 is with respect to our x-axis. So nandito yung EBC. So if we will vectorially get the difference between these two, we will have the resultant here. This is line EBC. And this negative 90 degrees, eto siya. Yung 30 degrees dito, eto yung angle, 30 degrees. Next one is your line ECA. So line ECA, the difference between EC and EA. So positive EC. So inenegate natin yung EA. Nandito yung negative EA. The resultant of these two will be here. Approximately here. So this is now your ECA. EC is 1 angle 120 minus 1 angle 0. So that is equal to 1 angle or square root of 3 angle 150. Square root of 3 angle 150. This 150 is with respect to x-axis. So nandito yung 150. This one. So as we analyze this phase voltage and phase currents, phase voltage and line voltages, we can see that the angle between the phase voltage and the line voltage is 30 degrees. So makita natin dito yung EA, ahead yung EAB ng 30 degrees with respect to EA. Yung EB, ahead yung EBC ng 30 degrees with respect to EB. So, saan natin nakuha tong 30 degrees? This is 120 from x-axis to EB is 120 minus this one is 90. So 120 minus 90 is 30 degrees. Again, the relationship of the phase voltage and the line voltage. The line voltage is ahead by 30 degrees to its phase voltage. So yung EA natin kanina, ito, ay 30 degrees with respect, yung EAB ahead ng 30 degrees with respect to its phase voltage EA. And also, your ECA is ahead by 30 degrees with respect to EC. So, saan natin nakuha yung 30 degrees dito? So, 150 from here, 150 minus, diba, our EA is 120 degrees with respect to AC. So, 150 minus 120 is 30 degrees. This one, EBC is also ahead by 30 degrees with respect to EB. So, from our reference x-axis, that is 120 to EB. So, 120 minus 90 degrees, that is 30 degrees. And also, the important formula is the line voltage is equal to the square root of 3 multiplied by its phase voltage. So, for the power, we have square root of 3 multiplied by line voltage times line current cosine theta, or your power factor. So, other formula is 3 times E phase, I phase cosine theta. The other one is P is equal to 3 times I phase squared R phase. For apparent power, this is the true power. For the apparent power, we have S is equal to square root of 3 ELIL, or 3 times E phase I phase, or that is the square root of P squared plus Q squared. This is for apparent power. Next one is your active volt ampere, Q. That is square root of 3 ELIL sine theta, 3 times E phase I phase sine theta, and from the power triangle, this is your S, Q, and this is P, and this one is your Q. So, Q will be the square root of S squared minus P squared. Same here in power, we have P is equal to square root of S squared minus Q squared. Example, a balanced star connected load of 8 plus J6 ohms per phase is connected to a balanced 3-phase 400 volt supply. Find the line current, power factor, power, and the total volt amperes. So if we are going to draw the circuit diagram of this problem, we have the sources here, and also the lines, which is, this one is A, not RYB. Line A, line B, and line C. Each line-to-line voltage is 400 volts. So, line voltages, EAB is 400 angle 0, EBC is 400 angle, this one is negative 120, and ECA is 400 angle positive 120. Then we are going to solve for the phase voltage of this problem. So phase voltage for Y connected load or Y connected system is equal to line voltage is equal to square root of 3 multiplied by the phase voltage. Its current is I phase equal to line current for Y connection. So E phase is equal to 400 divided by square root of 3, that is 231 volts. Its magnitude only, but if we will consider its magnitude and directions, we will have EA is equal to 231 angle 0, EB is 231 angle negative 120, or 231 angle 240 volts. EC is 231 angle 120 or 231 angle negative 240 volts. Next one, if we are going to consider only the magnitude, we have impedance is equal to square root of 8 squared plus 6 squared, that is 10 ohms. So the first required in the problem is we are going to solve for the line current. Line current is equal to the phase current equal to 231 divided by 10, which is 23.1 amperes. So it has a magnitude only. But if we want to get the magnitude and direction, we will consider the currents. For IA, we have 231 angle 0 divided by 8 plus J6. That is 23.1 angle negative 36.87. For IB, 231 angle negative 120 divided by the impedance, which is 23.1 angle 83.13 degrees ampere. So this is wrong. That is 231 angle negative 120 divided by 8 plus 6i. That is angle negative 156 dapat. Negative 156.87. This one is .1 angle positive 83.13 degrees ampere. So if we are going to draw the vector diagram of the voltage, phase voltage and phase currents, we have the reference is in phase with the phase voltage EA. EC is 120 degrees apart with respect to EA, and also EB is 120 degrees apart with respect to EA. EB and C is also 120 degrees. Now, our IA is placed by negative 36.87 with respect to the reference. So this is negative 36.87. IB is negative 156. So ito yung negative 156.87. And the last one is positive 83.13. So this one is 83.13 degrees. As you can see, they have the same magnitudes, 23.1, but they are not in the same directions. So for the power factor, letter B, we can solve that one by R over Z. 8 divided by 10, that is 0.8 lagging. Lagging because, as you can see here, the voltage at yung current, mas nauuna yung voltage kesa yung current. So yung current yung nahuhuli. So that's why it has a lagging power factor. For the power, you can solve this one with different formulas. You can use square root of 3. Square root of 3 because it is a three-phase system multiplied by the line voltage, line current, cosine theta. And also you can use multiplied by 3, but the difference is you will use the phase voltage instead of the phase of the line voltage. So 3 times phase voltage times phase current cosine theta. But you will get the same power. So this one is times 3, not square root of 3. 3 times I phase squared R. You will get 12.8 kilowatts. For the apparent power S, you will have square root of 3 EL IL or 3 times E phase I phase. That is equal to square root of 3 400 times 23.1 equal to 16 kVA. Second example, 3 equal star-connected inductors. Take 8 kilowatt at power factor of 0.8 when connected across a 460 volts. 3-phase, 3-wire supply. Find the circuit constants of the load per phase. So this circuit constants of the load will be your R and XL since this is an inductive load. So you cannot say that this is a pure inductance because you have a power factor of 0.8. Okay, so our total power is 8 kilowatts. Power factor of 0.8 lagging. Line voltage is 460 volts and we are required to solve for R phase and XL phase. Our total power is equal to square root of 3 ELIL cosine theta, and we can solve your line current. That is equal to 8,000 divided by square root of 3 times the line voltage, 460 times 0.8. That is 12.55 amperes. This angle is the arc cosine of 0.8 lagging, so that's why it is negative 36.87 degrees ampere. We can solve now your per phase impedance. That is equal to, we need to solve the E phase because our parameters here are already in per phase. So dapat naka per phase din yung voltage. EL divided by square root of 3 divided by I phase. In Y connection, I phase and IL are equal. So 460 divided by square root of 3 divided by 12.55 angle negative 36.87. So you will get a rectangular form which is 16.93 plus J 12.697 ohms. Therefore, this is your R and this will be your J XL. The per phase equivalent now of your system is R phase equal to 16.93 ohms and XL per phase is J 12.697 ohms. Next example, when the 3 identical star-connected coils are supplied with 440 volts 50 Hz 3-phase supply, the single-phase wattmeter whose current coil is connected in line R and pressure coil across the phase R and the neutral reads 6 kilowatts and the ammeter connected in R phase reads 30 amperes. Assuming, so we will use ABC phase sequence, find the resistance and reactance of the coil, reactive power of 3-phase load, and the power factor of the load. So this is our circuit diagram. We have a 3-phase which has a load, impedance load per phase. So wattmeter composed of an ammeter which is in series with the line This one, current coil is your ammeter and the pressure coil is your voltmeter. The voltmeter is connected at line A and neutral. And as you can see, this wattmeter is a single phase. So wattmeter is equal to 6 kilowatts. And for the single phase wattmeter, we have P is equal to E phase or E phase I phase cosine theta, or simply EI cosine theta. Now, how can we solve the resistance and reactance of the coil? First one, since our line voltage is in between phase line A and line B, so we must compute the phase voltage. Kasi ang kailangan natin ay yung phase voltage. Since our IA, which is 30 amperes connected in R phase, so ibahin na lang natin to yung R, IA, Y, IB, and RYB. Line B is line C. So this is RYB or ABC. So the current in ammeter reads 30 amperes. Next, para makuha natin yung resistance and reactance from the formula P is equal to EI cosine theta, we can solve first the cosine theta or the power factor, which is power equal to power divided by EI. So 6,000 divided by the phase voltage, which is 254 volts, times the current which is 30 amperes. That is 0.787 power factor lagging. And then, using the Ohm's law, E is equal to IZ, we can solve your impedance equal to 254 divided by 30, that is 8.47 ohms. So, power factor is equal to R over Z. Solving the resistance, that is power factor times the impedance, equal to 6.66 ohms. Solving now your inductive reactance, that is the square root of Z squared minus R squared, that is J 5.23 ohms. Now, the second one is we are going to solve for power factor. So, nasolve na natin. Power factor is equal to 0.787 lagging. Theta is equal to R cosine of the power factor, which is 38.09 degrees. The third one is solving the reactive volt ampere. This one. Reactive power or reactive volt ampere. That is Q equal to square root of 3 ELIL sine theta. So, square root of 3 times the line voltage, which is 440, times the line current, 30 amperes. The sine of your angle, which is 38.09, so sine 38.09. You will get 14.04 kVAR.